Angular acceleration. So for angular acceleration, I have to consider the velocity at different time intervals. But in general, I am now consider the instantaneous angular velocities. Of the particle P at time t and also at time t plus delta t are given by at time t the instantaneous velocity is omega vector and at time t plus delta t the velocity is omega plus delta omega. So by the definition of average acceleration, here I am denoting the average angular acceleration as alpha. And if you remember in the previous article, in the figure, the direction of average angular acceleration was shown. You can also see that video. Here, the value of average acceleration we have to consider as the change in angular velocities, or we can say the instantaneous angular velocities divided by the time interval. So the change in velocities means the final angular velocities minus initial angular velocity divided by the time interval. So final time was t plus delta t and initial time was t, and hence the final equation for average angular acceleration alpha vector is equals to delta omega vector divided by delta t. So this is my first equation for average angular acceleration. Same, we are applying the instantaneous property over here. Then for instantaneous angular acceleration, alpha vector is equals to limit delta t tends to 0, delta omega divided by delta t, that is equals to d omega by dt. Now here, if you see, the direction of angular acceleration is same as the direction of angular velocity. So the directions are same, and hence in this particular case it is not necessary to determine the direction. But for SI unit we can find out the SI unit of average angular acceleration or the angular acceleration is the unit of angular velocity is radian per second divided by the time interval is also second. So the SI unit is radian per second square or rotation per second square. So this is the SI unit. So here we will found the relation between the linear and angular acceleration. As we know that the derivation of linear velocity means dv with respect to time means dt is equals to linear acceleration, and that is very equal to the value of angular acceleration by this way, omega into dr by dt plus r into d omega by dt. Now, from where does this relation comes? Because of v is equals to r cross omega, and as per the rule of differentiation, in the case of multiplication, we have to put one quantity as constant and to differentiate the another one. In addition to that, we now have to make constant the remaining one and to differentiate the omega term. So, with this effect, the above relation has been arrived. Now, not only this, if you remember, then this is the rate of change of position with respect to time. So, change in position is displacement with respect to time is nothing but linear velocity. Similarly, if you look around this equation, the rate of change of angular velocity with respect to time is nothing but the value of acceleration alpha. And with these quantities, now my equation for acceleration will become A is equals to omega cross V plus R cross alpha. So now if you look at the left hand side, then this is the linear acceleration, and the right hand side is containing the angular acceleration. So this is the relation what we have obtained. But to find out the radial component of linear acceleration, because now it is correlated with the angular acceleration. So what are the radial component of the linear acceleration vector A? So for that we now consider the motion of a rigid body, that means the one kind of rotational motion in this article. So here we have considered the rotational motion of a rigid body, which is containing of two vector components. The first one is acceleration, and the another one is omega cross V. Here the particle of the rigid body is rotating according to the right hand screw rule in the direction from omega to V. So see, this particle is containing of the two vector components. So the direction of circular path you can clearly see from this. This is the omega and this is the direction of V. So the object is rotating from omega toward V. And this omega cross V I can also write in terms of the angular form or the acceleration formed as alpha cross r. So both are having the same magnitude and same direction. But if you look at this particular quantity omega cross v is found to be the radial direction towards the center, and so this component is called the radial component. Of linear acceleration A, that is denoting the magnitude, and I can also write this radial component as AR, means A subscript R, as omega cross V. Its magnitude is given by omega V sine theta. So, suppose the value of theta is pi by 2. Then I can also find out its magnitude. So AR is equals to omega V. Now let us find out the tangential component of the linear acceleration. So for that again I am consider the motion of a rigid body in this way. So the actual value of the third component, that is tangential component, we can say that the component which is according to the tangent to the circular, and that you can easily observe that this alpha cross r means along this direction. So this alpha cross r is found to be the tangent of circle, or we can say to the circle, and hence this alpha cross r is called the tangential component of A, and I am denoting it as AT, where T stands for tangent. If you want to find out the magnitude, then for magnitude AT is equals to alpha r sine theta whenever the angle between these two vectors is pi by 2. So that is alpha r. So this is the magnitude of tangential component. Now the total linear acceleration is now can be written in the form of combination of its tangential component as well as its radial component. So here A is equals to AT plus AR. And if you want to find out again the magnitude of A, for which this tangential component and radial component are mutually perpendicular to each other, And so the value of magnitude of acceleration is given by under root of at square plus ar square. Now from equation 1 and 2 I can substitute the values of tangential component and radial component. So the value of tangential component was omega v and its square is omega square v square plus here alpha square r square. So this is the magnitude of linear acceleration. Suppose if you consider that the rigid body is moving with constant angular velocity, that means the time is changing but the velocity is not changing. So for that, the value of angular acceleration will be 0. And so the value of alpha is equals to 0 and hence the tangential component of acceleration will also be 0. But the radial component will be as it is, and so the value of centripetal acceleration in uniform circular motion, if you remember, that was v square upon r. So this is due to the reason what we have discussed over here. Now, if you see in this discussion that the angular displacement means theta, the angular velocity means omega, and the angular acceleration alpha are equal for all particles of the rigid body. And the characteristic of theta, omega and alpha are called the variables of the rotational kinematic. So these three are now known as the variables of rotational kinematics. See why they have used this word rotational kinematics. This is because of here till now we have not discussed any kind of reason that why such motion occurs. So they have written over here kinematics. Now the description of motion of a particle of a rigid body is giving us the information about the linear variables. So what are the linear variables? Means position vector, linear velocity, linear acceleration, and is also true for the rotational variables theta, omega and alpha. But when all the particles of the rigid body are to be considered, then the rotational variable may be used for the entire body description because all the particles are invariant inside the rigid body. Now we will solve an illustration related to this particular